right, so we're going to talk about improving our soil test phosphorus recommendations to get for greater precision. We have great precision in our ability to apply nutrients, but I want to talk more about the prescription, the recommendation that goes behind them. And the impetus behind this should be fairly obvious, but with more precise recommendations, we are able then to maximize agronomic production, efficiency, economics, and also reduce potential non-point losses of phosphorus. So there's a lot of good reasons to improve the precision and accuracy of our soil phosphorus testing. So we'll start out by talking about how current soil testing works. So it's empirical. All right, so that means it's simply based on a correlation. So you have your soil test extractant, whatever it might be, depending on your region, Bray, Malick, Olson, Morgan's, whatever it is, and you extract that. You get a certain concentration of phosphorus as a result, and that is correlated to the yield, right? So obviously, see if I get this pointer working. Not that it, yeah, okay. You can see from the figure as the amount of extractable phosphorus in the soil increases, clearly you increase yield until you get to some point where when you continue to increase soil phosphorus, extractable soil phosphorus, it plateaus. You no longer get an increase in yield. We call that the critical level, and that's traditionally that's the target of your target soil level. So for Malick 3, for example, that's considered somewhere around 20 to 30 milligrams of phosphorus per kilogram of soil. Okay, that's how it works. It's simply just based on that empirical relationship between soil test phosphorus and yield. But in reality, when you look at the actual data that goes behind it, it looks more like this. All right, let me go back one there. It looks more like that, and I'm being generous here. That it's actually much more scattered than that. So you have a huge variability in the data, and the reality of it is that depending on your soil type, depending on your conditions, the relationship might look like this. It could look like there, very different critical levels. It could look something like that, just depending on the conditions and the soils. You don't know, because those soil test recommendations are based on the average of everything, average conditions, average soils. It's all lumped together, which works okay, but it's not precise. And so what we're talking about today is alternatives to that to become more precise. I want to read a quote from Dr. Stanley Barber from his book, Soil Nutrient Bioavailability. This is the guy who, much of what we understand about how plants take up nutrients, we know it because of him. He wrote in his book regarding empirical soil testing, which is what we currently have, versus taking a mechanistic approach. He said that the most commonly used tests extract some portion of the labile soil phosphorus pool. However, when different soils are used, solution phosphorus concentration, buffer capacity, and diffusion rate may not be correlated. Therefore, any one of the values would not be correlated with predicted phosphorus uptake, and the simpler soil test, which is the traditional test, would not be more reliable. So in other words, what that means is that when you base these on the average, take an empirical approach, sometimes you're going to over-apply, sometimes you're going to under-apply, because very rarely is our soil going to be the average of what those recommendations were based on. Here's the consequence of that. This illustrates the consequence of what he wrote. Here's real data from is in North Carolina or South Carolina. This is soybean yield as a function of soil test phosphorus, and they determined the critical level on these different soils. So we have 3 different soils that were being tested here. A heavy clay soil on the far left, medium texture in the middle, and a sandy soil on the right. And what you'll notice is that the critical level varied. There was no constant critical level for soil test phosphorus that was necessary to maximize your yield. Instead, what they show is that for the heavy clay soil, you needed about 9 pounds. You needed about 9. Wow. Okay. Why did I just hit it once? Can we put me back to that slide I was on, that's possible. There, thank you. All right, let's try this again. If I point it that way. All right, so about 9 pounds per acre is what you need in that heavy clay soil to reach maximum yield. But in the medium textured soil, you needed more. You needed 18 pounds of phosphorus per acre in that soil to reach maximum yield. And for the sandy soil, you needed 27 pounds. So the critical value varied depending on the soil properties. All right. So before we get into a discussion on this alternative approach, which is more mechanistic, less empirical, we need to understand how the plant actually takes up nutrients. I'm going to illustrate that here with a figure. So the storehouse for your nutrients is the soil, of course, and you've got, we categorize it broadly. You've got two main pools of nutrients in the soil, particularly for phosphorus. You've got labile and non-labile phosphorus. Non-labile nutrients are those that are bound very, very tightly, and they don't go into solution very easily. And it's an equilibrium with the pool known as we call it the labile pool. And the labile soil phosphorus pool is just the nutrients that are held much more weak. And that pool, that soil-bound pool, is in equilibrium with the solution. So we can dissolve it. The soil releases it from the labile pool into the solution. And once that nutrient is in solution, then the plant can take it up, okay? Plants do not take up nutrients from the soil. They take it up from solution. The soil is simply there as a storehouse, okay? We illustrate the same thing in this figure here. We have I'm getting a little bit of feedback here. Try moving that way. We have the solid soil surface retains the nutrients, and then they're in equilibrium with the solution. They supply the solution. We call that the quantity-intensity relationship. It's the ability of the soil to buffer nutrients, particularly phosphorus. But once it's in solution, then the plant is able to take it up. Okay, so plants take up nutrients directly from solution, takes up phosphorus from solution. The uptake of phosphorus from solution by a plant is a function of the solution phosphorus concentration. That should seem fairly obvious. But it's also a function of the ability of that soil to keep replenishing that solution, to keep resupplying it every time it gets depleted. Again, that's the quantity intensity. The storehouse of the nutrient is the quantity. The concentration in solution that the plant actually has access to is the intensity. And there's three ways for phosphorus particularly to be taken up, or more correctly, there's three ways for phosphorus to move to the surface of a root where the root can actually take it up. First one is root interception. Second one is bulk flow. Bulk flow is simply whatever phosphorus happens to be dissolved in the water that a plant is taking up, that phosphorus goes up with it as well. Third one is most important, diffusion. Almost all of your phosphorus that's taken up by a plant is through the process, it gets to the plant root through the process of diffusion, and it is irregardless of water uptake by the plant. It is highly dependent upon the location of phosphorus. It is a very short-range mechanism. The phosphorus has to be very close to the plant root, within 2 millimeters. I can illustrate it here. What you have is a concentration gradient that allows diffusion to occur. It allows that phosphorus to move from higher concentrations located farther away from the root. At the surface of the root, the phosphorus concentrations are lower because the plant's taking it up. And through that gradient, it's exaggerated here. In reality, it's less than 2 millimeters. But through that gradient, phosphorus diffuses towards the surface of the root, again, very slowly, and it's over a very short range. We can describe it with this equation using a Fick's law. And then once it's at the surface of the root, the plant can take it up. And we can describe that as well through the various kinetics equations. So we can take into account all these different mechanisms of nutrient uptake with this equation here. This is known as the Barber-Cushman model, and it takes into account bulk flow, diffusion, and then the plant actually taking it up. So this was a very important discovery development, I should say, 1980, this equation was solved in the transient state by a mathematician at Purdue in cooperation with Dr. Barber. But it gave them a tool. It gave plant physiologists a tool to be able to mechanistically quantify and predict the uptake of nutrients. It's not just a simple correlation like what we have for soil testing. It's a true mechanistic model that considers the physical reality of what is happening in the soil and the plant. So something else that we know is that different plants require different concentrations of phosphorus in solution in order to meet the required P mass, the required mass of phosphorus to be taken up to reach maximum yield. They call this the external phosphorus requirement. So for example, corn, it was in the 1970s, this is from a textbook actually, soil fertility textbook, they said, well, corn, you got to have about, I don't know what it is, like 0.02, I can't read it from here, 0.02 milligrams per liter of phosphorus in solution to reach max yield, but you need something like 0.2 for beans to reach max yield. And there's a problem with that. The problem is, and that sounds good, and that was true for their experiments, but the problem with that is it's a moving target. Yes, the plant takes up phosphorus directly from solution, but that target concentration in solution, it's not a fixed concentration. It actually varies. Is it 0.2 milligrams per liter in solution? Is that what's necessary? Well, sometimes it depends on your soil. And the problem was we were treating this as a static value for too long. A lot of the scientists and the soil scientists in the 70s, and myself included, if we understood more about the dynamics of it and the reality of how it's taken up, like Dr. Barber did, we would have known better. So instead, we were chasing after this target that was moving and treating something that was multidimensional with one dimension, in one dimension, assuming that it was just a static required concentration. Let me give you an example of that. Actually, before I give you an example of that, I want to say that what I'm proposing as a solution to that in using a mechanistic model is that we need to be multidimensional. And I'm proposing that we utilize the Barber-Cushman model to pinpoint the location of that moving target so we know where that target is located, because it's going to vary depending on your soil characteristics. So why should we use a mechanistic model like this? One, because it's mechanistic. All right, so it can either directly or indirectly take into account your differences between soil properties and soil conditions. Another reason is because it allows us to take a mass balance approach. And that's important because consider that what ultimately matters is that it's a finite mass of phosphorus, or any nutrient for that matter, that needs to be taken up into the plant biomass in order to attain maximum yield. So that mass requirement of phosphorus is universal. It doesn't matter what soil you're on. You have a certain crop variety, certain type of crop, certain variety. If it requires 600 milligrams, it needs to get 600 milligrams. It doesn't matter how it gets it, how the soil supplies it. It needs to get that much into the plant. So that takes a moving target and sticks it in one place, okay? Let me give you an example of that. So, like I said, the mass of P required is going to be universal across soils, but the soil can supply it dynamically. So let's say that a corn plant needs 550 milligrams of phosphorus to reach maximum yield, okay? Over 120 days. It's got to take up that 550 milligrams over 120 days. And let's say this soil here on the left, it has a soil phosphorus pool. We call it the quantity, and it's in equilibrium with the solution, and it's able to supply the solution pool and release about 0.8 milligrams of phosphorus per liter. If it did that, the plant would have to, once it's released the solution, the plant takes it up. The soil would have to keep resupplying that solution pool 19 times a day in order to meet that 550 milligrams, okay? But that doesn't mean that's the only way to do it. Take the soil on the right. Let's say that this soil is only able to supply the solution, solution concentration of 0.2 milligrams per liter, much less. You might say, well, we're not going to meet that requirement of 550 milligrams getting that into the plant. Not necessarily. If that soil can keep replenishing that solution pool 76 times a day, you're still going to meet your 550 milligrams after 120 days. So it's dynamic. The target of 550 milligrams is static. Okay? So the question then is, how much soil-bound phosphorus do we need to meet that mass requirement by the plant? Well, it depends, as I showed in that last slide, it depends on the ability of that soil to supply the solution P. How often, how quickly can it replenish it? And can it keep replenishing it to the same concentration? That's the quantity-intensity relationship. That's the buffer capacity of the soil, its ability to keep supplying the solution pool. And that is going to vary as a function of soil properties, mineralogy, pH, organic matter, all that good stuff. Obviously, it's also going to depend on the total amount of phosphorus you have in the soil, because you can't supply a solution pool if you don't have phosphorus there in the first place, right? You can't make something out of nothing. It also depends on the physical location of that phosphorus. Remember, diffusion's the dominant mechanism. Therefore, the phosphorus has to be located very close to the roots in order for it to be taken up. So our current fertilizer recommendations, they're based on results from a soil test extraction, like Mehlich or Bray, and from soils taken from 0 to 6 inches, which is not representative of no-till conditions, has a big impact on the location of that phosphorus. And there's no consideration currently for soil type or conditions. You just get one relationship, and if your soil's different, you're either over-applying or under-applying. There's no consideration for crop varieties. That may or may not be important. So in an ideal mechanistic approach, think of it as having two arms. All right, so you've got on the left side, you've got some quantification of the ability of that soil to supply phosphorus into the solution. And then once it's in solution, on the right-hand side, the other arm comes down that quantifies the ability of that phosphorus to move from point A to the surface of the root so it can be taken up. At the heart of it, in the center, is the mass requirement of phosphorus. How much phosphorus needs to get into that plant? What mass has to get into that plant to reach maximum yield? So then all of that together, it's possible then to make a shortcut to determine how much you actually need in the soil. So our current soil testing, like I said, is empirical. It doesn't consider that. It doesn't consider mass balance. It's just based on a correlation between an extract concentration and yield. It doesn't consider any of those things. It considers quantity or fertilizer relationships somewhat, and it simply makes a somewhat poorly informed shortcut from there. It's not terrible, but we can do better. It does okay. So at the end of the day, the plant demands a finite mass of phosphorus to be taken up by the roots in order to reach maximum grain yield. So the question is, based on the specific conditions and management of that soil, what concentration of soil test extracted phosphorus do you need to meet the mass demand of that plant? Because it's going to vary depending on your soil. So our current phosphorus recommendations, they're not bad. They get us in the ballpark. They're not precise, but there's a lot of room for improvement, which could save a lot of money and also potentially reduce phosphorus losses to surface waters. So the long-term goal on this, and this is going to take years, okay, is to utilize and improve the Barber-Cushman model to develop more precise phosphorus recommendations that are soil and condition specific. So in order to do this, we need to determine what is the required P mass for various cultivars. We need to know what are the plant uptake kinetics for different plants. And then we need to incorporate root modeling, because a lot of it comes down to the surface area of the roots, since the dominant mechanism is indeed diffusion. So my vision is that we will indeed continue to use soil test phosphorus extractants like your Mehlichs and your Brays and your Olsen, but vary the optimum level, your critical target level, as a function of soil properties and management. So the first step to this is to determine what is that required mass of phosphorus that needs to be in the plant to hit max yield. So I'm going to show you some data from that right now. We started out with corn, now we're working on with beans. I'll show you some of the corn data. So in order to do this, we optimize conditions. We built an indoor growth chamber, and we did not use soil, all right? I don't want to use soil. I want to separate the soil from the plant because the two confound each other. Soils absorb nutrients, that they release them later. I want to have total control in these experiments of the solution concentration, because remember, plants take up nutrients directly from solution. So what we have here is a system. It's basically a sand culture, hydroponics. So we're optimizing the conditions. We're supplying all the non-phosphorus nutrients in adequate amounts, and everything else is adequate. The light, the moisture, temperature, everything. And then we add a range of phosphorus from low to high to determine the minimum mass of phosphorus that needs to be taken up to reach maximum yield. And we used 3 cultivars. We wanted to compare 3 different cultivars and see if that required mass of phosphorus, if it varied between cultivars. And so in order to separate the soil from the plant, we used a nearly 100% pure quartz silica sand. The reason why I use that is because it will not absorb any nutrients. All right? It won't absorb any nutrients and won't release any nutrients. Whatever I apply in the irrigation, in the drip irrigation, is exactly what the plant root will see, if they could see. It'll be the root environment. So it allowed me to very precisely control the conditions. All right, let me show you some of the results. So first of all, there is no significant interaction between the phosphorus treatment and the variety for yield components. That's good. That means I can average across the different cultivars. So that was very helpful. So you'll see the data I'm showing you. I don't have to have a whole mess of points. I can average across them. All right, as you'd expect, as you increase the amount of phosphorus that you add, the more it takes up, the higher yield. Okay, no revelation there. To a point. And I'll show you that in some detail here. Okay, now at maximum yield, the phosphorus use efficiency was similar among the varieties. But as it was approaching yield, there were some differences. Pioneer was the most phosphorus use efficient, followed by Dynagrow and then the decal varieties that we were testing. And there were also differences in overall production. In general, the Pioneer produced more than the Dynagrow, which was more than the decal. All right, here's some data. So what we're showing here is the grain yield expressed as a function of phosphorus uptake per plant. All right, so you can see pretty clearly that as the plant takes up more phosphorus, the grain yield increases, okay, to a point. All right, so you get to about, once the plant takes up around somewhere between 0.55 and 0.63 grams of phosphorus, the yield plateaus, the grain yield plateaus. The plant will continue to keep taking up more phosphorus, but you're not getting any more grain yield out of it. All right, let's show the same thing for the total biomass, not just the grain, but the total biomass. Even after the plant has plateaued in yield, after it's taken up about 0.6 grams of phosphorus, like I said, it keeps taking it up, and the biomass keeps increasing. Even though the grain yield plateaus, the biomass keeps increasing, but even that plateaus as well. The total biomass plateaus around 0.8 grams. Once that plant takes up 0.8 grams of phosphorus, you're not getting any more biomass out of it either. So in both cases, this is a perfect illustration of luxury consumption. The plant can take up more phosphorus than it needs to attain maximum grain yield and even maximum biomass as well. Okay. It's interesting to look at how phosphorus was distributed in that plant, in those plants, as it continued to take up more and more phosphorus. So on the x-axis here, what you have is you guys can't see that. I'll just tell you. On the x-axis, what you have is the total phosphorus uptake. So on the far left, you've got the treatments that took up the least phosphorus, and on the right, you have the highest phosphorus uptake. And the bars, within each bar, describes the percentage distribution of phosphorus within that plant. So the big purple bars that dominate most of it that's the percent phosphorus in the grain. All right. So what you see is that at the lower uptake, when the plant, only takes up around 300 milligrams, it's putting almost all of that phosphorus right into the grain. And as the plant takes up more and more, it's putting a lower percentage into the grain, and it's sticking more of a percentage into an increasing percentage, I should say, into the stem, cob, and tassel. Okay, so you see the purple bars get smaller and smaller. It's putting less percentage-wise. That's a percentage of phosphorus into the grain. When it's starving for phosphorus, it's putting everything into the grain. It just wants to reproduce, right? It wants to survive. Now, the numbers on it, and I know you can't see those probably very well, but the numbers on it are the absolute mass of phosphorus that's taken up. So we see that the mass of phosphorus that goes into the grain gets higher and higher as well, and it maximizes somewhere around 580, 590 milligrams in the grain, and that also corresponds to where the plateau in yield is. So in other words, once you get about 580 milligrams of phosphorus into that grain, you hit max yield, and that's it. It's going to start putting that phosphorus somewhere else. It's not going to put it in the grain anymore. It's going to put it into the stem, cob, and tassel. So a good way to think of it is this. Essentially what we did is your grain yield is set by your genetic potential. So you can think of your genetic potential as an empty bucket. And so depending on the genetics of your corn, you have varying sizes of genetic potential. You have different size of empty buckets, right? And then your job as a producer is to fill that bucket. And the more you fill that bucket, the greater grain yield that you'll get. Okay, so here's the thing. So what do they say? Your max, for a lot of varieties, they say that the max grain yield is 600, the number I heard was 612 bushels per acre, all right? So that's what you start out. That's the max. And then depending on the environment, temperature, moisture, light, nutrients, you change the size of that bucket. It can get smaller. It can't get any bigger. The bucket can only get smaller. So depending on the conditions, those buckets get smaller. All right, and then as a producer, your job is to fill that bucket. So you fill that bucket as a function of temperature, light, moisture, and fertility. And you start to fill that bucket, and the more you fill that bucket, the greater your grain yield. Okay? And eventually, though, you can fill that bucket up. And once you fill it, that's it. That's your max yield. That's what we did. All right? We maxed out grain yield. Once we got around 580 milligrams of phosphorus into that grain, we hit max grain yield. Once that plant took up around 0.63 milligrams of phosphorus, you filled that bucket completely. It's going to start sticking that phosphorus into other plant parts. That's it. How's that data compare to real field data? This is 100 years worth of data. This is from a paper from CMPD and Vine. They got about 100 years worth of corn data, and it's all conditions, right? It's all different kinds of varieties. It's all conditions. It's the good, the bad, and the ugly. And this is where our data falls on it. All right? So we're at the very top of it, top of yield, which makes sense because we had optimum conditions. But if you notice, the shape of our data fits that data as well, and it suggests that there is indeed a max nutrient uptake per plant to hit max yield. So there's the data again by itself. Instead of fitting it to a power curve like they have there, if you follow that black dashed line, they show a power curve, which is inappropriate. That doesn't really describe how a plant works. It will not infinitely take up phosphorus and keep increasing yield. Instead, it plateaus, right? So here's our data. That's how you actually, that actually describes the physical reality of the plant. It takes up phosphorus to a point and you hit max yield, and then that's it. All right, so if you take that type of curve, take that shape of our curve and apply it to their data, it looks something like this. It agrees with it pretty well, actually. You're hitting max yield after that plant, after that corn takes up around 0.6, 0.65 grams of phosphorus. You're maxed out. Okay. So the easy part's done. We need to get somewhere around 0.6 grams of phosphorus into a corn plant over 120 days to reach max yield. You put any more than that into the plant, it's luxury consumption. The hard part then is next. Knowing that that's our target, how do we adjust soil concentrations so that it can supply, for a specific set of conditions, so that it can supply 0.6 grams into that plant. And the problem is that's going to be hard to determine because it's a moving target. We're doing this for beans as well right now. Maybe next year I'll have data to report on that.